We begin in the dark. Take a moment to let the stillness settle around you. Let the noise of the day, the rushing of hours, and the clutter of immediate concerns drift away like leaves carried off by a slow-moving river. There is nowhere else you need to be right now. There is nothing else you need to solve. There is only the quiet and the vast, inviting canvas of the imagination. Imagine you are standing on a grassy hill on a clear, moonless night. The air is cool and crisp, carrying the scent of damp earth and sleeping pine. Above you, the sky is not just a ceiling, but a limitless depth. It is a velvet curtain pulled back to reveal the true nature of our reality. It is a sea of diamonds frozen in silence. For thousands of years, we have stood on hills just like this one, looking up. We have traced shapes in the stars, naming them after hunters, queens, and beasts. We have used them to navigate our ships across earthly oceans. But mostly, we have looked up with a single haunting question echoing in the chambers of our minds: are we alone? It is a question that feels both terrifying and hopeful. In the vastness of the cosmos, in a universe that stretches for billions of light years, are we the only ones who look up? Are we the only ones who feel, who dream, who wonder? For a long time, the answer was silence. We shouted into the void with radio waves, and the void did not answer. We built great telescopes of glass and metal, peering into the gloom, and saw only rock, gas, and fire. The universe seemed beautiful, yes, but undeniably dead. It seemed like a magnificent, empty house waiting for inhabitants that never arrived. But the universe is old, and our patience is young. As we learned to look closer, to look deeper, and to look differently, the picture began to change. We stopped looking just for stars and started looking for the shadows dancing around them. We began to find planets, first a few, then hundreds, then thousands, and among them, hidden in the constellation of Leo, roughly 120 light-years away from where you sit right now, there is a world that has changed everything. It is a world that does not look like Earth, yet it whispers the same secret. It is a distant, alien sphere where the chemistry of the atmosphere has spoken to us across the dark gulf of space. Current data suggests that this planet has a 99% chance of possessing the building blocks of life. It is a staggering thought. 99%. In the world of science, which usually deals in cautious probabilities and margins of error, this number is a thunderclap. It suggests that the loneliness we have felt as a species might be an illusion. It suggests that life is not a miraculous accident confined to a single blue marble, but perhaps a cosmic inevitable. Let us go there. Let us leave the grassy hill and the familiar constellations behind. We are going to travel across the light years, not in a spaceship of metal and fuel, but on the silent wings of thought. We're going to visit this world, to float in its skies, to drift over its boundless oceans, and to understand why this specific point of light has given us such profound hope. As we rise from the Earth, the blue glow of our home fades into the starfield. We pass the moon, a silent grey sentinel. We drift past the angry red eye of Mars and the golden swirling storms of Jupiter. We leave our solar system behind, passing the icy scattered stones of the Kuiper Belt, until our sun is just another bright star in the distance, no brighter than Sirius or Vega. We are now in deep space. The silence here is absolute. It is a heavy, thick silence, a peace that has existed for eons. The darkness is not empty. It is a fabric woven with gravity and light. To reach our destination, we must travel 120 years at the speed of light. That is a distance that the human mind struggles to comprehend. If you could fly a commercial jet to this planet, it would take over 100 million years to arrive. But here, in the realm of the narrative, we cross that abyss in a heartbeat. Ahead of us, a star grows brighter. It is not a yellow star like our sun. It is smaller, cooler, and redder. It is a red dwarf, the most common type of star in the universe. These stars are the quiet, long-lived embers of the cosmos. While our sun will burn for 10 billion years, this star will burn for trillions. It will watch the rest of the universe grow dark and cold. It is a patient star. And orbiting this patient star is the world we have come to see. It is known by the Catalog designation K218b, a name that sounds robotic and cold, hardly befitting a world that might harbor the warmth of life. So let us simply call it the ocean world. As we approach, the planet looms large in our vision. It is massive, more than 8 times the mass of the Earth. It is a category of planet known as a sub-Neptune, a bridge between the rocky worlds like Earth and the gas giants like Neptune. For a long time, astronomers thought such worlds would be uninhabitable, thick balls of suffocating gas with no surface to stand on. But this world is different. As we drift closer, we see no cratered grey rock. We see no swirling storms of toxic green. Instead, we are greeted by a deep, dark blue. It is a blue that seems to absorb the starlight, a blue of infinite depth. This planet is covered by a global ocean. There are no continents here, no islands breaking the surface, no mountains climbing into the clouds. There is only water stretching from pole to pole, a continuous, unbroken skin of liquid. It is a Hycean world. The word Hycean is a blend of hydrogen and ocean. It describes a planet with a hot, hydrogen-rich atmosphere blanketing a massive liquid water ocean. It is a type of environment we do not have in our own solar system, a reminder that the universe is far more creative than we are. Float here for a moment in the upper atmosphere of this alien world. The sky above is not blue, but a hazy, reddish-cream color, the result of the red sun's light filtering through the thick hydrogen clouds. It is a perpetual twilight. The star hangs large in the sky, casting a soft, ruddy glow over the cloud tops. Below us lies the ocean. It is not like the Atlantic or the Pacific. It is warmer, perhaps hot enough to cook in, yet the immense pressure keeps it liquid. It is a cauldron of chemistry. Why do we say there is a 99% chance? What did we see that made our hearts skip a beat? It wasn't a radio signal. It wasn't a photograph of a city at night. It was something far more subtle and perhaps far more profound. It was a fingerprint in the light. When the planet passes in front of its red star, the starlight filters through the planet's atmosphere before reaching our telescopes. As the light passes through the air, the different gases in the atmosphere absorb specific colors of the spectrum. It is like a barcode. By reading the missing colors, we can tell exactly what the air is made of. We looked at this barcode with our most advanced eyes, the James Webb Space Telescope. We saw the signature of hydrogen. We saw the signature of carbon dioxide. We saw the signature of methane. These molecules tell us that underneath the clouds there is likely liquid water. But methane and carbon dioxide alone do not prove life. They can be produced by volcanoes, by rocks, by lightning. But then, deep in the data, buried in the noise, we saw a ghost. A faint, tentative signal of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced by only one thing: life. It is not made by rocks. It is not made by volcanoes. It is made by phytoplankton. It is the smell of the seaside, the pungent, salty aroma of low tide. It is the scent of the living ocean. To find this molecule in the atmosphere of a distant world is the equivalent of walking through a vast, sterile desert and finding a single, fresh rose petal lying on the sand. It shouldn't be there unless something is growing. The presence of this molecule is the 99%. It is the whisper that suggests beneath the thick, hazy clouds, in that endless, warm, dark ocean, something is alive. Let us descend further. Let us sink beneath the cloud deck of this Hycean world and understand the architecture of this potential miracle. We often think of life as fragile. We look at the delicate petals of a flower or the soft skin of a newborn, and we think that life is a precarious thing, easily extinguished. And in a way, it is. But life is also tenacious. It is stubborn. It is chemistry that wants to happen. To understand why this planet is so promising, we must understand the concept of the Goldilocks zone, or the habitable zone. This is the narrow band around a star where the temperature is just right, not too hot and not too cold for liquid water to exist. If a planet is too close to its star, the water boils away into steam, leaving a dry, scorched rock like Venus. If it is too far, the water freezes into ice, creating a frozen wasteland like Mars. But in the middle, in that sweet, temperate band, water can flow. And where water flows, life can swim. K218b sits perfectly in this zone, but it does so differently than Earth. Because its star is a red dwarf, much cooler than our Sun, the habitable zone is much closer in. This planet hugs its star, completing a full orbit, a full year in just 33 days. If you lived here, you would celebrate a birthday every month. Because it is so close, the star looms large in the sky, 3 times larger than the Sun looks from Earth. But because the star is dim, the light is gentle. It is a world of eternal, soft afternoon. But there is another factor that makes this world unique, a factor that changes the rules of habitability. It is the atmosphere. Earth has a thin atmosphere, mostly nitrogen and oxygen. It is like a light blanket, but K218b has a thick, heavy atmosphere of hydrogen. Hydrogen is a potent greenhouse gas. It traps heat efficiently. This means that even though the red sun is cool, the planet stays warm. The hydrogen acts like a down comforter, keeping the heat of the planet locked in. This thick blanket allows the ocean underneath to remain liquid at temperatures and pressures that would be impossible on Earth. It creates a massive global stability. On Earth, we have ice ages and heat waves. We have seasons that freeze and thaw. On this ocean world, the temperature likely remains constant, a steady, warm bath that has lasted for billions of years. Think of the stability of that environment. Billions of years of uninterrupted warmth. Billions of years for molecules to bump into each other, to combine, to learn to replicate. Let's descend now through the hydrogen haze. As we drop through the clouds, the red light of the star fades into a deep purple gloom. The pressure builds, the air is thick and heavy. And then we hit the surface. It is not a crashing impact, but a merging. The boundary between the thick atmosphere and the ocean is not sharp like it is on Earth. It is a gradual transition. The gas becomes denser and denser until it is a supercritical fluid, and then, finally, liquid water. Imagine an ocean with no bottom, or rather, an ocean so deep that the bottom is irrelevant to the life swimming above. On Earth, the deepest point is the Mariana Trench, 7 miles down. On this world, the ocean could be hundreds of miles deep. At the bottom of Earth's ocean, high pressure turns water into a crushing force. But here, the pressure is even more immense. Deep down, hundreds of miles below the surface, the water might be compressed into a strange form of hot ice, exotic phases of ice that do not exist in nature on Earth. This high-pressure ice creates a mantle, separating the liquid ocean from the rocky core below. This separation is important. On Earth, the ocean touches the rock. Minerals from the rock leach into the water, providing food for life. We call this the carbon-silicate cycle. It is Earth's thermostat. Critics of the High-Sean theory worry that if the ocean is separated from the rock by a layer of high-pressure ice, perhaps the water is too pure. Perhaps it is starved of nutrients, perhaps it is a sterile aquarium. But the universe is clever, life finds a way. Even if the bottom is sealed off, there is dust falling from space. There are chemical reactions in the atmosphere raining down organic compounds. Methane, ammonia, the building blocks of proteins, the sky feeds the ocean. And remember the dimethyl sulfide, the molecule of life. If that signal is real, and the 99% probability suggests the data is strong, then something in this water is consuming energy and excreting waste. Close your eyes and try to imagine what lives here. We must be careful not to populate this alien sea with earthly monsters. There are likely no whales here, no sharks, no silver schools of tuna. Evolution on a hydrogen-rich world would take a different path. The life here would need to survive in water that might be significantly warmer than Earth's oceans. They would need to withstand higher pressures. Perhaps they are microbial, trillions upon trillions of tiny organisms floating in the upper layers of the sea, soaking up the dim red light of the star, converting the hydrogen and carbon dioxide into energy. A global soup of living dust. Or perhaps, given the stability of the eons, they have grown. Imagine vast gelatinous sheets of life drifting in the currents like living curtains. Imagine balloon-like creatures filled with hydrogen to maintain buoyancy, floating between the liquid and the gas, grazing on the chemical rain. There are no eyes here, perhaps. In the murky depths beneath the thick clouds, vision might be less useful than other senses. Perhaps they sense electrical fields, perhaps they communicate through vibration, sending thrumming songs across the global ocean. A song that never ends, encircling the world in a chorus of existence. The silence of space is broken here, not by human voices, but by the churning of water and the biological hum of a living planet. It is a world where the water never breaks against a shore. There is no sand, there are no trees, there is no fire. There is only the fluid, the drift, the eternal bath. It is a womb the size of a planet, and it is not alone. K2-18b is just the first of its kind. We have analyzed in such depth. It is the prototype. If Hycean worlds are real, they might be much more common than Earth-like worlds. We have spent decades looking for Earth too. So, a rocky planet with thin air and continents. We have been looking for a mirror of ourselves. We have been looking for the familiar. But the universe is telling us that we should have been looking for the unfamiliar. The most common type of star is the red dwarf. The most common type of planet is the sub-Neptune. It stands to reason then that the most common type of life in the universe might not be the frantic, land-walking, fire-burning life of Earth. The most common life might be the quiet, drifting, dreaming life of the Hycean seas. The 99% probability is not just a number. It is a paradigm shift. It tells us that life is not the exception. The dead universe we thought we lived in was only dead because we were looking at it through the wrong lens. We were looking for reflections when we should have been looking for shadows. As we hover over this endless ocean, watching the red sun dip lower in the eternal twilight, we must confront the feeling that arises from this knowledge. For generations, humanity has suffered from a cosmic form of isolation, anxiety. We have felt tiny, insignificant, and terribly lonely. We have looked at the cold stars and felt ignored. But if this planet is alive, if the smell of the sea drifts through the atmosphere of K2-18b, then the galaxy is not a graveyard. It is a garden. It is a garden where the flowers bloom in the dark. It is a garden where the soil is made of water and gas. It is a garden that does not need us to tend it. It has been flourishing on its own long before we climbed down from the trees, and it will continue long after we are gone. This realization is not frightening. It is comforting. It takes the burden of specialness off our shoulders. We do not have to carry the torch of life alone. We are just one candle in a vast cathedral full of light, but there is more to explore here. We have touched the water and we have smelled the air, but we have not yet looked at the time. We have not yet considered the history of this world and the future that awaits it. The red dwarf star that warms this ocean is billions of years older than our sun. This planet has existed for a stretch of time that turns mountains to dust. What kind of evolution happens over 10 billion years? What kind of complexity arises when the environment never changes, never freezes, never boils? Is it possible that the life here is not just slime and bacteria? Is it possible that beneath the waves there is intelligence? Not an intelligence that builds cities and rockets, but an intelligence of the deep, a philosophy of the water. We will drift deeper into these questions. We will explore the implications of a universe teeming with Hycean worlds. We will look at how we found this place and what it means for our future. To understand the magnitude of this discovery, we must step back from the alien ocean for a moment. We must travel back across the 120 light years back towards Earth, but stopping just short of home. We come to a place in the emptiness known as the second Lagrange point. It is a lonely spot, 1,000,000 miles from Earth, hovering in the perpetual shadow of our planet. Here, the temperature is almost absolute zero, the silence is profound, and floating in this frozen quiet is a machine of exquisite beauty. It looks like a ship from a dream. It rests on a sunshield the size of a tennis court, 5 layers of silver stretching out to block the heat of the sun. And rising from this shield is a honeycomb of gold. 18 hexagonal mirrors coated in the purest gold, joined together to form a single massive eye. This is the James Webb Space Telescope. It is the most sensitive instrument humanity has ever built. It is a time machine designed to catch light that has been traveling since the dawn of the universe. It is so precise that it could detect the heat signature of a bumblebee on the moon as seen from Earth. It was this golden eye that turned its gaze toward the constellation of Leo. It was this machine that stared at the dim red star K2-18, waiting for the planet to cross in front of it. The method we use to find the 99% signal is a testament to human ingenuity. We cannot see the planet itself. Even with our best technology, K2-18b is too far away, too dim, and too close to the glare of its parent star to be taken as a photograph. We cannot see the waves, or the clouds, or the color of the water directly. So, we watch the shadow. Imagine you are standing in a dark room, looking at a bright light bulb. Now, imagine a moth flies in front of the bulb. For a split second, the light dims. You can't see the details of the moth's wings, but you know it is there because of the shadow it casts. This is called a transit. When K2-18b passes in front of its red sun, the starlight dims by a tiny fraction. But we do more than just measure the dimming. We analyze the light itself. As the planet passes in front of the star, a tiny ring of the star's light skims through the planet's atmosphere on its way to us. It passes through the clouds, through the hydrogen haze, and through the mysteries of that alien air. As the light travels through the atmosphere, the molecules floating there interact with it. Different gases eat different colors of light. Water vapor absorbs one frequency, methane absorbs another. Carbon dioxide absorbs yet another. When the light finally reaches the golden mirrors of the telescope, millions of miles away, it carries a stamp. It carries the chemical fingerprint of the air it passed through. We take that light and spread it out into a spectrum, a rainbow of data. We look for gaps. We look for the missing colors. These gaps are the signatures of the molecules. For hours, the telescope stared. It collected photons one by one, gathering them like precious raindrops in a drought. It sent this data back to Earth, a stream of ones and zeros traveling through the dark. And on the screens of scientists, a graph appeared. It was a squiggly line, rising and falling. To the untrained eye, it looked like noise. But to the astronomers, it was a symphony. There were the peaks for methane. There were the peaks for carbon dioxide. These confirmed the High nature, a hydrogen sky over a water world. But then there was that other wiggle in the line, that faint shy bump in the data. The spectral signature of dimethyl sulfide. It is difficult to convey how delicate this measurement is. We are looking for the chemical trace of a gas that might make up only a tiny fraction of the atmosphere on a planet hundreds of trillions of miles away by looking at the shadow it casts on a star. It is like trying to see a puff of smoke from a cigarette in Tokyo while standing in New York by watching how it changes the color of a street lamp behind it. And yet, the signal was there. The scientific community is cautious. They are the guardians of truth, and they do not make claims lightly. They say, potential detection. They say, strong evidence. They talk about confidence intervals, but the number that emerged, the statistical likelihood that the signal is real and not just random noise, hovered at that breathtaking 99% mark. It is important to sit with the weight of this. We are not just looking at rocks and gas anymore. We are looking at the metabolic exhaust of a planet. We are seeing the breath of a world. If you were an alien astronomer looking at Earth from light years away, you would see oxygen and methane together. That combination is unstable. They react and destroy each other. The only reason they exist together in our air is that life is constantly pumping them out. Life keeps the chemistry of Earth off balance. We see a similar imbalance on K2-18b. The chemistry suggests that the ocean is doing something. It is active. It is churning. This golden eye in the dark, floating in the silence of the Lagrange point, has given us a mirror. It has shown us that the universe is not just a collection of physics equations. It is a place of chemistry that wants to wake up. As we turn our thoughts back to the planet, we must appreciate the bridge we have built. A bridge made of glass, gold, and mathematics, connecting our curiosity to the secrets of a distant star. It is a fragile connection, but it is enough to change how we see our place in the cosmos. Let us return to the surface of the ocean world. Let us float once more in the eternal twilight with the great red sun hanging heavy in the hazy sky. To understand the life that might exist here, we must understand the star that feeds it. K2-18 is a red dwarf, an M-dwarf star. These are the runts of the stellar litter. They are much smaller than our sun, much cooler and much dimmer. To the naked eye, our sun is a blinding white-yellow diamond. This star is a warm, glowing ember. But what they lack in brightness, they make up for in longevity. Our sun is a yellow dwarf. It burns bright and fast. It was born about 4.5 billion years ago, and in another 5 billion years it will swell up, swallow the Earth, and then die, fading into a white dwarf. The entire story of Earth, from the first microbe to the last human, must fit within this brief 10 billion year window. We are creatures of a temporary star, but a red dwarf. A red dwarf burns its fuel so slowly, so efficiently, that it can live for trillions of years. Think of that number, trillions. The universe itself is only 14 billion years old. K2-18 is just a baby in the grand scheme of its own lifespan. It will continue to shine steady and red long after our sun has died. It will shine long after the Milky Way has merged with the Andromeda galaxy. It will shine until the very end of the stellar era of the cosmos. This means that K2-18b, the ocean world, is a planet with an almost infinite future. If life has started here, it does not have a deadline. It does not have to rush. On Earth, evolution feels like a race against time. The sun gets hotter, the climate shifts, the window of habitability closes. But here, the window stays open. However, there is a price to pay for this immortality. Red dwarfs are temperamental in their youth. Because they are smaller, their magnetic fields are tangled and violent. They are prone to stellar flares, massive eruptions of radiation that can scour a solar system. For a rocky planet like Mars or Earth orbiting close to a red dwarf, these flares can be deadly. They can strip away the atmosphere. They can bathe the surface in sterilizing X-rays. They can turn a habitable world into a barren rock in the blink of a cosmic eye. This is why many astronomers were skeptical of finding life around these stars. They called it the red dwarf paradox. How can life survive in a shooting gallery? But K2-18b has a secret weapon. It has a shield. Remember the ocean. Water is one of the best shields against radiation in the universe. On Earth, spent nuclear fuel rods are stored in pools of water. The water absorbs the radiation, glowing with a soft blue light, but keeping the surroundings safe. On the ocean world, the life does not live on the surface. It lives deep down, beneath the waves. When the red sun flares, when the storm of radiation lashes against the planet, the thick hydrogen atmosphere absorbs the first blow. It might glow with immense auroras, ribbons of neon pink and green dancing across the entire sky. And what gets through the air strikes the water. The top few meters of the ocean might be sterilized, but 10 meters down, 20 meters down, the radiation cannot reach. The creatures of the deep are safe. They might sense the flare as a brightening of the surface, a sudden shimmer in the twilight, but they are untouched. The ocean protects them. It cradles them. This dynamic creates a fascinating possibility for evolution. On Earth, mass extinctions usually come from the sky. An asteroid, a burst of gamma rays, a shift in the sun. These events hit the reset button, wiping out the dominant species and allowing new ones to rise. The dinosaurs fell and the mammals rose. But on a Hycean world, the ocean buffers the planet against these cosmic tantrums. The environment below might remain stable for billions of years, uninterrupted. What happens to evolution when you don't hit the reset button? On Earth, we are the product of chaos. We are adaptable, scrappy, and quick-thinking because we had to survive ice ages and meteor strikes. We are the children of catastrophe. But the life on K2-18b might be the children of peace. Without the constant threat of extinction, evolution might not favor speed or aggression. It might favor efficiency. It might favor size. It might favor symbiosis. Imagine creatures that grow for centuries, accumulating wisdom in their genetic code. Imagine ecosystems where every organism is perfectly recycled, a closed loop of harmony that has been refined over eons. This is the concept of slow life. We tend to measure intelligence by technology. Can they build a radio? Can they split the atom? But these are technologies of fire and rock. You cannot build a fire underwater. You cannot smelt iron in the deep ocean. So, perhaps their intelligence is not technological, but biological. Maybe they have mastered genetic engineering not with tools, but with their own bodies. Maybe they can change their shape, their color, their chemistry at will. Maybe they have developed a collective consciousness, a neural network connected by chemical signals in the water, where the ocean itself acts as a giant brain. The red dwarf star, shining dimly above, gives them all the time in the world to perfect this existence. We look at this planet and we wonder if they are advanced. But perhaps we are the primitive ones. We are the ones rushing around, burning our resources, fighting for survival on a rock that is slowly heating up. They are the ones floating in a warm, eternal bath, protected by a global ocean, watched over by a star that will essentially never die. It brings a new meaning to the word habitable. We usually mean survivable. But K2-18b might be more than survivable. It might be a paradise of stability, a cosmic sanctuary. As we consider this deep time, we must also consider the layout of the planet itself. We know it has an ocean, but what lies beneath? The structure of K2-18b is alien to us. We have a thin crust over a mantle of magma. K2-18b likely has a liquid ocean that transitions into ice VIs, or ice VI5 forms of ice that exist only under crushing pressure. This ice is not cold, it is hot, black and hard as rock. This mantle of hot ice separates the living ocean from the rocky core. This separation is what makes the stability so complete. There are no volcanoes spewing ash into the ocean. There are no shifting tectonic plates causing earthquakes. The floor of the ocean is a solid, smooth sheet of exotic crystal. It is a world designed for silence. And yet, in that silence, under the gaze of the long-lived star, the chemistry of life has seemingly found a foothold. The molecule dimethyl sulfide is the messenger. It tells us that the stillness is not empty. It tells us that in the quiet, protected dark, something is breathing. As we prepare to delve into the final leg of our journey, we must ask, if this world is so perfect, so stable, and so common, why haven't we heard from them? If life is 99% likely here, and there are billions of planets like this, where are the signals? Where are the greetings? Perhaps the answer lies in the water itself. Perhaps the nature of a Hycean world keeps its children home, forever dreaming in the deep, unaware of the stars above the clouds. Or perhaps they simply have no need for the noise of the universe. If life is so probable, if the chemistry of the cosmos is practically begging to create existence, then we must confront the final, haunting silence. Why haven't they called? If K2-18b is one of billions of Hycean worlds, and if these worlds have been stable for 10 billion years, surely life there has had time to grow, to learn, and to reach out. Surely they should have filled the galaxy with their signals by now. But the radio telescopes are quiet. The night remains dark. This brings us to a concept known as the water trap. To understand it, we must look at our own history. How did humans reach the stars? How did we build the Voyager probes and the James Webb Space Telescope? It started with fire. Fire is the primary tool of technology. With fire, we learned to cook food, which gave our brains the energy to grow. With fire, we learned to smelt ore, turning rock into copper, bronze, and iron. With fire, we created steam, powering engines. With fire, we manipulated silicon to build the computer chips that run our world. But you cannot light a fire underwater. On the ocean world of K2-18b, the inhabitants live in a realm where open combustion is physically impossible. They cannot smelt metals, they cannot blow glass to make lenses for telescopes, they cannot build circuit boards. They might be incredibly intelligent, They might have brains larger than ours, capable of complex language, mathematics, and profound emotional depth. They might have a culture rich in poetry, song, and philosophy. They might know the secrets of their own biology better than we ever will, but they will likely never build a radio. They are trapped in their paradise. The very water that protects them from the radiation of the red dwarf also insulates them from the progress of technology as we define it. They are destined to remain in their cradle, forever swimming in the dark, warm waters, unaware of the vast universe above them. And it is not just the water that isolates them, it is the sky itself. Remember the thick, hazy hydrogen atmosphere. On Earth, we have clear nights where the Milky Way spills across the dark like a river of diamonds. This view inspired every astronomer, every navigator, every dreamer in human history. It made us want to go up. But on K2-18b, the sky is a perpetual cloudy twilight. They likely cannot see the stars. They cannot see the other planets in their system. To an inhabitant of this world, the universe consists only of the endless ocean and the great dim light above. They do not know there is an outside. This realization changes how we view the silence of the universe. It suggests that the galaxy might be teeming with life, but it is a galaxy of introverts. It suggests that intelligent civilizations are not expanding empires hungry for conquest and colonization. Instead, they are isolated pockets of consciousness, locked away in their cloudy bubbles, dreaming their own dreams, separated by the immense gulfs of interstellar space. We, the people of Earth, might be the anomalies. We are the ones on the dry, dangerous rock, forced to master fire and metal to survive. We are the ones who can see the stars, and therefore we are the ones who are lonely enough to reach out. The 99% on K2-18b might not be a civilization of engineers. They might be a civilization of whales. Think of the whales in our own oceans. They have existed for millions of years. They sing complex songs that travel for thousands of miles. They have tight-knit families and emotional lives. But they have no desire to leave the water. They have no need to build cities. They are content. Perhaps the ocean world is a planet of 10 billion poets singing into the deep, their voices vibrating through the high-pressure ice, creating a symphony that no one outside will ever hear. This thought is bittersweet. It means we might never shake hands with them. We might never exchange knowledge. But it also means that they are safe. They are safe from the troubles that plague technological civilizations. They will never pollute their atmosphere with smoke. They will never accidentally create a weapon that destroys their world. They will simply exist in harmony with their eternal ocean until their star finally fades. There is a dignity in that silence, a quiet perfection. The signal of dimethyl sulfide we detected is not a distress call. It is not a greeting. It is simply the byproduct of living. It is the universe breathing. And for now, that is enough. We have traveled far in our minds. We have crossed the light years to the constellation of Leo. We have dived into the hydrogen clouds. We have swum in the boundless dark ocean. We have contemplated the rise and fall of civilizations that will never know our names. Now, it is time to return. Drift back up through the heavy atmosphere of K2-18b. Watch the red sun shrink into a star. Watch the planet recede until it is just a speck of light, lost in the glare of the red dwarf. Float back across the emptiness, past the silent dust of the cosmos, until you see a familiar blue shine. Land gently back on the grassy hill where we started. Feel the solid earth beneath your feet. Smell the pine and the damp soil. Look up once more at the night sky. The stars look the same as they did an hour ago. The patterns haven't changed, but you have changed. Before, the sky looked like a cold, empty ceiling. It looked like a lonely place. But now, when you look at that vast field of darkness, you know that somewhere out there, hidden in the glare of a red star, there is a scent of the seaside. There is a world where the waves never stop rolling. There is a world where life, tenacious, stubborn, beautiful life, is likely flourishing in the deep. The number 99% is not just a statistic, it is a permission slip. It is permission to believe that we are not a cosmic accident. For so long we have asked, are we alone? The answer, whispering from the atmosphere of a distant world, seems to be a gentle, reassuring number. We are not alone. We are just distant neighbors. We are like two people living in different houses on a vast, dark plain. We cannot see each other. We cannot hear each other. We may never meet. But we can see the light in each other's windows. And knowing that the light is on, knowing that someone else is home, makes the darkness feel a little less overwhelming. This discovery reminds us of our own fragility and our own luck. We live on a rare world where fire is possible, where the air is clear, where we can see the universe and wonder about it. We are the eyes of the cosmos. We are the universe waking up to perceive itself. The creatures of K2-18b may be the dreamers, safe in their warm ocean. But we are the voyagers. It is our burden and our privilege to look up, to search and to know. Take a breath of the cool night air. It is the same air that sustains you, just as the hydrogen air sustains them. It is all chemistry. It is all stardust. It is all life. The universe is not dead. It is holding its breath. And in the silence between the stars, if you listen closely enough, you can almost hear the heartbeat of a living cosmos. You are part of that heartbeat. You are part of the 99%. We have rested on the hill. We have accepted the possibility. But the human mind is not content with 99%. We crave the absolute. We crave the 100. So, where do we go from here? How do we cross that final agonizing gap between very likely and undeniable truth? The story of K2-18b does not end with the James Webb Space Telescope. That golden eye was merely the scout. The heavy infantry is coming. Right now, in the high, dry desert of Atacama in Chile, a cathedral of science is rising from the dust. It is called the ELT, the Extremely Large Telescope. The name is simple, but the machine is monstrous. While the Webb telescope has a mirror spanning 6.5 meters, the ELT will have a mirror 39 meters across. It is a bucket for light so massive it could gather enough photons to see the streetlights of a city on the moon. When this great eye opens, later in this decade, it will turn towards the constellation of Leo. It will not just look at the shadow of the planet, it will attempt to take a direct picture. To photograph a planet next to a star is like trying to photograph a firefly next to a lighthouse beam from 10 miles away. It requires a technology called a coronagraph, a mask that blocks out the star, creating an artificial eclipse inside the telescope. If the ELT can block the red glare of K2-18, we might see a tiny faint pixel of light. That pixel is the planet itself. And in that pixel lies the truth. We will be able to see if the atmosphere changes with the seasons. We will be able to see if the methane levels rise and fall with a biological rhythm. We might even be able to detect the glint of the ocean, the reflection of the star off the liquid surface, the same way the sun glitters on the Pacific. But there is another mission on the horizon, one designed specifically for this moment. It is called the Habitable Worlds Observatory. Unlike the Webb, which is a generalist looking at everything from the Big Bang to black holes, this future telescope is a specialist. It is a hunter. It is being designed with one goal, to find Earth too. It will carry sensors capable of detecting techno-signatures. This is where the science borders on science fiction. A techno-signature is not a gas produced by bacteria. It is a gas produced by industry. CFCs, chlorofluorocarbons. On Earth, these are the chemicals we used in refrigerators and hairspray that damaged the ozone layer. They do not exist in nature. If we find CFCs in the atmosphere of K2-18b, the debate is over. Bacteria do not build refrigerators. If we find nitrogen dioxide, a byproduct of burning fuel, it suggests machines. The coming decades will transform K2-18b from a graph on a screen into a tangible world. We will map its clouds, we will model its currents, we will likely give it a real name, something more poetic than a catalogue number. Perhaps Oceanus or Thalassa or Viridia. We are building the architecture of belief, brick by brick, lens by lens. We are preparing ourselves for the moment the news breaks, not as a probability, but as a fact. Let us push the timeline further. Let us push past the telescopes. We know it is there. We know it is alive. The question, are we alone, has been answered. The new question is, can we reach them? Earlier, we spoke of the immense distance, 120 light-years. In the scale of the universe, this is next door. But to a human body, it is an insurmountable wall. With our current rockets, chemical engines that burn fire, the journey would take hundreds of thousands of years. Civilizations on Earth would rise and fall a dozen times before the ship arrived. But physics offers a loophole. It is not a wormhole or warp drive, it is a sail. Light has no mass, but it has momentum. When light hits a reflective surface, it pushes. It is a tiny, ghostly push, but in the vacuum of space, it adds up. This is the concept behind Project Starshot. Imagine a spacecraft, not a giant ship with hallways and sleeping pods, but a chip. A wafer of silicon, no larger than a postage stamp, weighing less than a gram. This chip contains cameras, sensors, navigation, and a transmitter. Attached to this chip is a sail, a sheet of material incredibly thin, incredibly light, and incredibly reflective. We launch thousands of these chips into orbit around Earth. Then, on the ground, we turn on the lasers. Gigantic arrays of lasers beam up, focusing their combined power on the sail. For a few minutes, the light hits the sail with the force of a space shuttle launch. The acceleration is violent. The chip goes from 0 to 20% of the speed of light in minutes. At this speed, 60 million meters per second, the journey to K218b shrinks. It no longer takes 1,000,000 years, it takes 600 years. 600 years is still a long time. It is the time between the Middle Ages and today, but it is manageable. It is a time scale that a civilization can plan for. We could launch a fleet of these starships today. For 6 centuries, they would silently coast through the dark, frozen sleepers in the void. And then, in the year 2625, they would arrive. They would streak through the K218 system. They would not stop. They are moving too fast to slow down. They would have mere hours to collect data as they fly by. But in those hours, they would snap close-up photographs. They would taste the outer atmosphere. They would listen for radio whispers. And then they would turn their tiny transmitters back toward the pale yellow dot of the sun and beam the data home. Another 600 years for the signal to return. By the year 3225, humanity, or whatever we have become, would receive the package. Imagine the scene. A future descendant of ours, sitting in a room filled with light, opening a file that was sent a millennium ago. The image loads. It is grainy. It is blurry, but it is there. A picture of the waves, a picture of the clouds from above, and perhaps, just perhaps, a picture of something breaking the surface. A dark shape against the blue, a fin, a vessel, a floating city of biology. It is a long shot. It is a multi-generational prayer cast into the dark, but it is possible. The physics works, the engineering is within reach, the only thing required is the patience. And perhaps that is what the ocean world is teaching us. In a universe of red dwarfs that live for trillions of years, in a universe of slow, stable evolution, our hurry is our weakness. To understand the cosmos, we must learn to think like a mountain. We must learn to think like a star. We must plant trees whose shade we will never sit in. We must launch ships whose landing we will never see. K218b is not just a destination for our telescopes. It is a destination for our maturity as a species. It is waiting for us to grow up, to slow down, and to reach out with the steady hand of a species that intends to survive. The 99% chance of life is a mirror. It reflects our own potential. If life can thrive there, in the dark, warm pressure, then surely we can thrive here, in the light. Rest now, in the knowledge that the universe is fuller, deeper, and more beautiful than we ever dared to dream. The ocean of stars is not empty, It is just waiting for us to learn how to sail.